All right. I'm going to try to respond to some of these questions. Modular arithmetic is important for cryptography and number theory. What are there other applications of modular arithmetic? Was there something you learned during your never-ending journey of studying math that shocked you in terms of modular arithmetic? Math shows up in all areas of life, and for some reason I feel like modular arithmetic might show up in some weird aspect of the real world, but I'm not sure what, where, why it does. I do think the most interesting applications are cryptography. So, for example, the Enigma machine. This was the machine that the Germans used in World War II to code their messages. And Alan Turing, a mathematician, cracked the Enigma machine code using modular arithmetic, mod 26 for the letters of the alphabet. So that was a really cool application. Another kind of fun application that I like is figuring out like the rules for division. So for example, does 9 divide 1,872? That one's actually kind of easy. How about something harder? 2,340. Oops. Don't worry, I know how to write numbers. And the answer is 9 does divide this because the sum of the digits is divisible by 9. And that seems kind of weird. But the idea of what's going on there is we can rewrite this as 2 times 1,000 plus 3 times 100 plus 4 times 10 plus 0 times 1. Right, and this is 2 times 10 cubed plus 3 times 10 squared plus 4 times 10 to the first plus 0 times 10 to the 0. This is just base 10 arithmetic. Now, what happens here is when you do, right, essentially we're trying to figure out if we, what's the remainder when we divide by 9? And the question is the remainder 0? Okay, is the remainder 0 when we divide by 9? And there are a bunch of theorems of modular arithmetic that you can build up that says, essentially, like, if we think about this congruent mod 9, we can rewrite this as 2 times whatever the remainder is when we divide 1,000 by 9. And the remainder is 1. Plus 3 times whatever the remainder is when we divide 100 by 9, which is 1. Plus 4 times whatever the remainder is when we divide 10 by 9, which is 1. Plus 0 plus 0. And then this is equal to just 2 plus 3 plus 4, which is congruent, which is, we just do the arithmetic, which is 9, which is congruent to 0. And this works, we can prove it using any number just by rewriting it as, in its power of 10 form. And so that's a quick way to figure out if a number is divisible by 9, just by adding up the digits. And the reason and the proof is requires modular arithmetic and some theorems about modular arithmetic. Is there another definition of modular addition we will use in this course? When proofs are difficult, and I feel an equivalent definition would make it easier. I am not planning on using one. The short answer is yes, there is another definition that we could use. We're probably not going to use it. And the reason why we're not going to use it is because it requires probably a day or two of like building up all of the framework to like really understand it. And with our current definition, there's no framework that we need. It's just the definition is understandable right off the get-go. So probably not, but there are other definitions out there. Let's see. Went over it briefly as example from theorem 2.8. So this was referring to Z P. I think this was referring to this when I looked up. This thing is a group when P is prime. So for example, if we did, right, pick any, let's pick Z5 star, right? So Z5 star is essentially just the non-zero elements, 1, 2, 3, 4. And we can make the multiplication table. 1, 2, 3, 4, 4. And you'll see it is a group and everything has an inverse. 2 times 2 is 4, 2 times 2 is 1, 3, 3 times 2 is 1, 3 times 3 is 4, it's 2, 3, 3 times 12, 2, 1. So that's an example, and then proving it is a little more challenging, but we could. Yeah, why does the definition of a group have associativity as a property but not commutativity? Because you said make something similar to a group that has commutativity as a property along with the identity and inverses, but not necessarily associativity. It would be useful to know because I've been wondering why associativity was chosen as a necessary property while commutativity was left out.
Okay. So this is a good question, and it's kind of hard to explain. Essentially, there was this famous mathematician, M.E. Noether. She's a female mathematician in the early 1900s, at a time when literally like women weren't allowed to study higher mathematics. So she had a lot of mathematical ideas, but she couldn't publish papers with her name on it. So there are a bunch of papers published that are essentially from her, but they have male authors' names on them. She wasn't allowed to take classes at university. She was only allowed to audit them. She wasn't allowed to teach classes, so she had to teach classes under a male mathematician's name. Anyway, so a whole bunch of roadblocks from allowing her to study mathematics, but she's still like one of the most influential mathematicians in the 20th century, because what she did is she used, she kind of like, she didn't totally invent group theory, but she pushed it way forward, and she was using group theory to explain physics, and essentially laid the foundation for like the conservation laws and quantum mechanics and things like that, using group theory. And essentially what she's doing is she's thinking about physics problems, and she's trying to understand symmetry, and in a real way, in the sense that, right, if you if you imagine a physical system and you like transform that system in the sense of like, well, let's just think about a three-dimensional system, and you have like some points in that system, and then you change the system in some way, like you shift the whole like image or picture to the right or to the left or in the z direction or in the negative z direction or whatever. What she was studying is ways to change these physical systems such that the underlying physics, like physical properties, like conservation of energy and things like that, don't change. Okay, so, and it turns out that these transformations that we're thinking about that leave like fundamental physics things unchanged form a group. In particular, they form, or in many ways, we're talking about Lie groups. And so now, what's a Lie group? Well, maybe we don't want to get into that, but essentially, the idea of these transformations is a lot of times in these physical systems we're doing more than one transformation, and we didn't want the order of the transformations to like matter, in the sense that if we were if we were using A and B and C to transform a system and they all conserved the physical like properties of reality, then it was really important that we could first transform the system, using A and B, or we could transform the system using B and C. So this is essentially why, one of the main reasons why associativity is so important is because we're thinking about these physical systems and transformations. And then it just kind of, then Emmy Noether abstracted it even further. So that's why associativity is so important. And there's something called a magma. So this is, even a more basic structure than a group. It's just a set S with binary operation. So it doesn't require associativity or inverses or identities or anything like that. Okay. And then there are, right, we can add in associativity and we get something called a semigroup. So it's a magma with associativity, or set S with binary with associative binary operation. And then we have a monoid, which gives us an identity. So set S with associative binary operation and identity. And then we get to a group, which we all know and love. And then we get to an abelian group. And so the question is, right, why did we leave out commutativity? And one reason is, right, in the world of physics, we are often dealing with matrices, and matrices are non-commutative. So if we required, if we're in the world of physics, which is where Emmy Noether was, taking commutativity as like, a basic foundation of these mathematical structures would get in the way of understanding a lot of things. In particular, get in the way of understanding, matrices. So hopefully that helps a little bit. If I show a function f from set A to set B is 1 to 1, what does that mean? A equals B. This is from question 5 of homework 1. Okay. So, good question. Let's say A, B, F. A and B are fine. And I guess I guess that's not enough. So if F is onto, then every element of, let's be a little more precise here, then for each B in B, there exists A in A such that F of A equals B, right? So everything over here, everything in B has a corresponding element, in A. And what this means is, I'll just say it and then I'll try to explain it some more, is that A has to have more elements than B. So this is cardinality, by the way. This is not, order. But if you're thinking about groups, you can think about it as order. So this is just how many elements the set B has. This is how many elements the set A has. So A has to have at least as many elements as B if our function is onto. And one way to think about that is if it didn't, right, if A had fewer elements than B, let's say that A had 2 elements and B had 3 elements, well, then that would mean that one thing in A would have to map to multiple things in B, and now we're no longer a function. Okay. So if a function is onto, we know that A has at least as many elements as B. Now, 1-to-1, so if F is 1-to-1, then each element in F of A, so this is the image of A, or the image of F. So these are essentially all the outputs, or the image of F, right? Because if it's 1-to-1, you don't necessarily hit everything in B, right? There could be some things that are left over. But if you're 1-to-1, then each element that is an image of F is mapped to by exactly one element in A. Or for, we could say more technically, for each B in, sometimes we write image of F, there exists a unique A in A such that F of A equals B. All right. And now what this tells us is that, right, B has at least as many elements as A. Right? Because everything that gets mapped to corresponds to only one, right? We don't like double up in a sense. If somehow, right? So imagine if B, here, let's make B smaller than A now, right? Let's imagine the opposite is true. If B was smaller than A, then there are 2 things in A that are going to have to map to B. Okay, so what we've just done, come on, go away, there we go. So if we're 1-to-1 and onto, what that means is that the number of elements in the domain is equal to the number of elements in the codomain. Okay, but this doesn't give us that A equals B yet. Okay, and the reason why in our proof, well, first of all, we're just dealing with finite, because dealing with infinite stuff is a little bit more complicated. But in our proof, we're going to show that, the cardinality of, there are just as many things in XG as there are in G. And then if we also show that XG is a subset of G, then these 2 ideas together, these give that xg equals g. Okay, you need, containment, either g contained in xg or xg contained in g, along with the fact that they're the same size. That gives you equality. And then I was talking to somebody else, just in case you don't like this, one-to-one and onto proof, you can also, right, you can also prove, right, to prove xg equals g, you can prove 1, that xg is a subset of g, and 2, g is a subset of xg. And then that will give you the same result. It's similar, it's similar, the reasoning is similar to the one-to-one and onto, but that's the way to do that. Hopefully that helps. Is that a question? Oh, wait, no. Oh, no, we answered that. Okay. That's it. Keep the questions coming.